Hello everyone, welcome back to my Chem Corner. In today's video, we're going to talk about another topic from the chapter Solutions. So before we move into the video, if you're new to this channel, please do subscribe to the channel and hit the bell icon so you receive notifications as and when I upload my video. So in today's video, we're going to talk about colligative properties. So here, there are many properties which can be related to decrease in vapor pressure. We've just seen in the previous videos when we talk about vapor pressure, what are the properties that are related to it? What are the reasons because of volatile nature and all of that, right? So we're going to learn properties related to this decrease in vapor pressure. So before we move into in detail, there are different types of colligative properties that we learn in this particular syllabus. The first one is going to be relative lowering of vapor pressure, depression and freezing point of the solvent, elevation of boiling point of the solvent, osmotic pressure of the solution. These are the four different types of colligative property that we will learn in detail. Now, when we learn about colligative property, what does colligative property actually mean? If there is a particular property on which number of solute particles are dependent on, which means anything that you take, the number of solute particles is something of prime importance. It is something that is considered. Then you call such kind of properties as colligative property. So that is all about the introduction of colligative property. Now we will go in detail about each of this colligative property. So in this video we are going to cover the first two types of colligative property, which is relative lowering of vapor pressure and depression and freezing point. So now the first one is relative lowering of vapor pressure. Now we're going to consider relative lowering of vapor pressure. Where does this decrease in vapor pressure come from? It all starts from Raoult's law. So as per Raoult's law, we've come across this particular formula there. P1 is equal to x1 into P1 naught, which you're going to mark as equation number 1. Now, as per the topic, it says reduction in the vapor pressure of a solvent is nothing but a difference in the pressure, right? So, delta P1 is equal to reduction in the vapor pressure of the solvent, which is P1 naught minus P1. Now, we all know that the value of P1 is given to you in equation 1. So, we're going to substitute instead of P1 this particular equation. So P1 naught minus x1 into P1 naught. Now we can take the common term out, which is P1 naught is equal to 1 minus x1. Name this as equation number 2. Now we can't further simplify this particular equation, but 1 minus x1 is nothing but x2. So instead of writing 1 minus x1, we can always write as x2 and name this as equation number 3. Now what we're going to do is we're going to rearrange the entire equation number 3. When we rearrange it, take out x2 mole fraction, then you will get delta P1 by P1 naught. Delta P1 we just calculated here, which is P1 naught minus P1. We just put it here. So we get it all a simplified equation in this case, and we're going to name this equation as equation number 4. Now x2 is nothing but the mole fraction of component 2. We can just expand the formula of x2, which can be written as number of moles of component 2 divided by number of moles of component 1 plus number of moles of component 2. So we just expanded that x2. Now, number of moles of component 1 is for solvent and number of moles for component 2 is nothing but for solute. So N1 is for solvent and N2 is for solute. Now, we've learned this even in equilibrium in first year, that in the denominator, we can ignore component 2, which can be neglected because they are lesser than component 1, and therefore we can simplify this particular equation as N2 by N1. So it's basically trying to simplify the entire equation. Now we just try to expand what is number of moles here. Number of moles is nothing but given weight by molar mass. Same thing for the component 2, and when you rearrange the formula, you get this final formula here. So here W1 is the weight of the solvent. W2 is the weight of the solute. M1 and M2 are molar mass of the solvent for M1. M2 is the molar mass of the solute. So whatever 1 you see, component 1, number of moles of the number of moles for component 1, weight of component 1, molar mass of component 1 is all for solvent. Whereas number of moles of component 2, molar mass of component 2 and weight of component 2 is nothing but for solute. Now we are going to use that particular last formula that we just wrote to calculate molar mass in a particular compound. We have problems related to it. So we are going to use this last formula to calculate certain things that are asked in the question. So for that, identifying W1, W2, M1, M2 is all important. So please remember, when you have component 1, it is for solvent and component 2 is for solute. So now this is a problem given to us. The vapor pressure of pure benzene at a certain temperature is 0.850 bar. A non-volatile, non-electrolyte solid is weighing 0.5 grams when added to 39.0 grams of benzene. Vapor pressure of the solution then is 0.845 bar. What is the molar mass of the solid? So there are a lot of values given to us because we have pure benzene here and we have a non-volatile, non-electrolyte solid which is a solute also. And there are some pressures also given to us. We need to now classify, we need to write down what is the given value and what are we asked to calculate. So first we will write what is given to us. P1 naught is given as 0.850 bar, which is the vapor pressure of pure benzene. P1 is 0.845 bar, which is the vapor pressure of the solution. That is given here. Now, after this, W2, which is for the solute, is given as 0.5. W1 is for solvent, that is given as 39 grams here. M1 is given to us as 78 grams because M1 is for benzene. Benzene, we all know that the molar mass of benzene is 78. If you don't know that by heart, you can always calculate it. Molar mass of benzene is 78. What is asked for us to calculate is the molar mass of the solid, which means for the solute. Now it's easy because everything is given to us from the formula, but we are asked to calculate M2. So it's easy. Now what we'll do is from the formula, you just have to substitute all the values and what you're left out with is only M2. When we try to simplify this first, the left hand side, and then try to simplify the entire thing, molar mass of the solute is given as 170 gram. So here, though the question looks bigger and a lot of random values here and there, it is easy for us to calculate once we can identify which is the solute, which is the solvent, what is W1, what is W2, and then it's easy for us to write down the entire points that are given to us and what is asked to calculate. Now the second one here is calculate the mass of a non-volatile solute whose molar mass is given to us, which is dissolved in 114 grams of C8H18 to reduce its vapor pressure to 80%. So same way, but only thing here is given in terms of percentage, so you need to come down to its pressure. So first, what is given to us? Total pressure is 100 bar. Out of that 100 bar, P1 is going to be 80 bar. Right? Now, from that, W2 is what we have to calculate. The question it is asked, mass of the non-volatile solute. Calculate the mass of non-volatile solute, which means W2 is what we have to calculate. Then what is given to us is W1. That is the mass of the solvent is given to us. Then molar mass of your solvent. We know what the solvent is, C8H18. It's easy for us to calculate what is the molar mass of it. Then the other molar mass M2 is also given to us. So M1 is for solvent and M2 is for solute. Now same thing again, put down the formula. Substitute whatever is given. What are you left with is only W2. When we simplify the entire thing, W2 is equal to 8 grams. Alright, so this way, first it's always easier for us whenever we have so many random values to substitute or to write down the values that are given to us in the problem, and then we write down what is being asked to us. Then in that case, it's easy for us to calculate the entire problem. Alright, now we move to the next topic, which is elevation and boiling point. Now, elevation and boiling point, we start with what is a boiling point of a pure solvent. That is denoted as TB naught because pure solvent. Right? Then you take the solution. Boiling point of the solution is denoted as just TB. Now a difference in the boiling point, because we can't have two different boiling points. So we need to take a difference. So difference in the boiling point is equal to TB minus TB naught, which is TB is the boiling point of the solution minus the boiling point of the pure solvent. Now what is a delta TB? The delta TB, yes, is the difference in the boiling point, but there's a term for it which is called as elevation of boiling point. Now for dilute solutions, which means you try and dilute the solutions a lot, the elevation of boiling point is directly proportional to molar concentration of the solute in the solution. So as you keep diluting your solution, what happens to the solute? The concentration of the solute is going to decrease more, right? You're making them more and more dilute. So here elevation in boiling point is directly proportional to the molar concentration of the solute in the solution. Okay, now when we tell that one, we can write it mathematically as the elevation boiling point directly proportional to molar concentration. Now to remove that proportional, we write out Kb as a constant here, and that is denoted as equation 1. Now what is that Kb? Kb is nothing but boiling point elevation constant, or it can be called as molar elevation constant, or it is called as ebullioscopic constant, any one term. Alright, now what is a unit of that Kb? When I take out Kb, I have delta Tb by molality. Delta Tb is obviously temperature, so the unit is going to be Kelvin. Molality, we know the SI unit is kg per mole, so you write down kg per mole over there. So here, when you look at the unit, this is going to be Kelvin kg per mole. That's going to be the unit of Kb. Now, when we look at molality, what is the formula of molality? Number of moles of solute by mass of solvent in kilogram. That is the formula of molality. So now what I'm going to do is I'm just going to write it mathematically. Number of moles of solute. Number of moles of solute is what when I expand it? Weight of the solute divided by molar mass of solute. And we all know solute is component 2 when we look at it. So it's going to be W2 by M2. Then we have mass of solvent in kilogram. So mass of solvent is what? W1 divided by 1000, because obviously whichever question we get, it's always going to be in grams only, whatever value you get. So you have to divide it by 1000, so you get it converted to kg. When I try to just simplify the entire thing, I'm going to get this entire formula, which is given as equation 2. Now what I'm going to do is I'm going to put this entire equation instead of m over here in equation number 1. So when I do that, I'm going to get this final equation that says delta Tb is equal to W2 into 1000 into Kb divided by M2 into W1. Now this part except for Kb is all molality. I've just substituted instead of M, I've put that entire equation there. Now that is the equation I'm going to use for further calculation. Now in most cases delta Tb will be given to us. You will be asked to calculate M2. So I've just rearranged the formula in such a way I'm taking out M2, delta Tb will be in the formula. So this is the formula you're going to use to calculate problems related to elevation and boiling point. Alright, so now we have a problem based on that. The boiling point of benzene is 353.23 Kelvin. When 1.80 grams of a non-volatile solute is dissolved in 90 grams of benzene, the boiling point is raised to 354.11 Kelvin. Calculate the molar mass of solute when Kb for benzene is 2.53 Kelvin kilogram mole inverse. Alright, so that is the question given to us. We have a lot of values in this. So first, before we jump into what we're supposed to calculate, let's write down what is given to us. Now what is given to us is delta Tb, which is the boiling point of the pure solvent. Nothing is done to it. It is a boiling point of pure solvent, so it's going to be Tb. So that is going to be 354.11 Kelvin. Now Tb naught is going to be of the solution, so it's going to be 353.23 Kelvin. So Tb and Tb naught here. Now W2 is going to be 1.80, which is for the weight of the solute. W1 is for the solvent, which is 90 grams. Kb is given to us. So in the formula, if you see, everything is given to us except for M2. That is what we are asked to calculate. But before that, we have two different temperatures. So what we are going to do is we are going to calculate what is delta Tb. Now when we calculate delta Tb, here we have to substitute the values, and we are going to find out what is delta Tb in this case. So it's going to be 0.88 Kelvin. Now once you have done that, write on the formula and do the substitution. So here you get W2, which is 1.8 grams, which is for your solute. Then we have 90 grams, which is for W1. When we substitute the entire thing, you will get 57.5 gram per mole. So basic thing is, it's just a direct substitution of the formula as long as you can understand or identify the values given to you in the question. Alright, so that is all about the problem in elevation and boiling point. Alright, so I hope this particular video has been helpful to each of you. In case you have any suggestions, please do write an email to me, or you can write in the comment box below, so I can read through it and I can answer your queries. I'll see you in the next video. Until then, take care.